AQA GCSE Chemistry Bond Energy Calculations. So we will start with reaction profiles, which you will have met before, bond energies, and then calculations using bond energies. So here is a typical reaction profile for an exothermic reaction, in that energy is released to the surroundings. The energy of the reactants is higher than the energy of the products. The difference is called the overall energy change, and that is released to the surroundings. So as the reactants have more energy than the products, the overall energy change is negative for an exothermic reaction. So here is the profile for an endothermic reaction. Here we have the products having more energy than the reactants. The difference is absorbed from the surroundings. Again, we call that the overall energy change, and as the products have more energy than the reactants in an endothermic change, the overall energy change is positive and is given a positive sign. What are bond energies? Well, every covalent bond has a bond energy value, and the idea is it's the input of energy required to break 1 mole of the bond. And as we're putting energy in, it's an endothermic change, and we give any bond energy values for breaking a positive sign. But in a data table, such as here, we will see that the bond energies aren't given a sign. It's up to you as a student to decide whether we're going to be breaking or making, because when a bond is made, energy must therefore be released. It's exothermic, and this, of course, has a negative sign. So although the data tables are without a sign, you're required to realize that if you're breaking bonds, you give that bond energy value for a particular mole of bonds a positive sign, whereas if you are making bonds, energy is released, and you give the bond energy value a negative sign. So let's move straight on to using bond energies in calculations. So bond energies are usually used to calculate the overall energy change in a reaction. And we break a chemical reaction down into 2 steps to allow us to do so. The breaking of the bonds in the reactants, that of course is endothermic, it absorbs energy, and then the making of the bonds in the products, that is exothermic, it releases energy. So if we look at an energy profile, our first stage is to break, and that of course will be endothermic, and then the second step is to make. So for an exothermic, we're going to break positive energy values, and we're going to make negative exothermic energy values. Exactly the same profile for an endothermic. The fact that it's endothermic does not change the fact that we are going to break all the bonds and then in the reactants and then make all the bonds in the products. Now, of course, this doesn't actually happen in a chemical reaction. This is a theoretical idea that enables us to calculate the overall energy change, the difference between the energy state of the reactants and the products. So if we break all the bonds and then make all the bonds, we can come up with pretty accurate assessment of the overall energy change, even though it's a theoretical process. So I'm going to model the method. Calculate the overall energy change for the reaction between hydrogen and chlorine to make 2 moles of hydrogen chloride. Well, I'm going to say the overall energy change is the energy for breaking all of the bonds and minus the energy released on making the bonds. So I'm going to account for the exothermic nature of the bonds being made by putting a negative in front of the bonds made energy values. So that formula will work very nicely. So, of course, breaking bonds has a positive energy value and making bonds has a negative energy value, and we build that into the equation by putting a negative sign in front of the bond energy values being made. So, what are the bonds that are broken? Well, I've got a hydrogen-hydrogen bond, 1 mole of. I've got chlorine-chlorine bond, 1 mole of. And then I've got a hydrogen-chlorine bond. But I haven't got 1 mole, I've got 2 moles. So the bond energy values are per mole, they're molar figures. So 1 times the hydrogen-hydrogen, 1 times the chlorine-chlorine, and 2 times the hydrogen-chlorine, sorry. Of course, we're keeping a negative sign in front of the bond energy values being made in the products. Now, from a data source, I find that hydrogen is 432, chlorine is 242. Hydrogen chlorine is 427 kilojoules per mole, but I'm multiplying that by 2. Sum that all together comes to minus 180 kilojoules per mole. So the overall energy change for this reaction is minus 180 kilojoules per mole. The fact that it's negative tells us that more energy is released than is absorbed. Making the bonds releases more energy than was required to break the bonds in the reactants. And therefore the reaction is exothermic, and that of course is indicated by the negative sign for the overall energy change. So in words, we may be asked to reply, what does this value mean? Well, it means that more energy is released on making the bonds in the products than is absorbed in breaking in the reactants. The reaction is exothermic and it has a negative sign. Try this problem. Calculate the overall energy change for the reaction between hydrogen and oxygen to make water. Here is a table of bond energy values. Pause and complete the calculation. Come back to check and correct when you are ready. Okay, so I'm going to reveal how I've carried out the calculation. First of all, and these are very often provided for you in the exam paper, I've analysed the reactants for the bonds present. I've got a hydrogen-hydrogen bond, but I've got 2 moles. I've got an oxygen-oxygen double bond, so O2 contains a double covalent bond. Then in water, we've got oxygen-hydrogen, oxygen-hydrogen, so 2 oxygen hydrogens in each water molecule, but I've got 2 moles of water molecules, so I multiply that by 2. So if I now analyze the bonds broken, well, from this table, hydrogen is 432, so I've multiplied that by 2, comes to 864. The oxygen double, make sure you use the right energy value, 495. And that totals plus 1359. I've given it a positive sign because breaking bonds is endothermic. So we give the bonds broken a positive energy value. And then the bonds made, well, in total, I've got 4 oxygen-hydrogen bonds, 2 in each water molecule, but 2 moles of water molecules. So 4 moles of oxygen-hydrogen covalent bonds. 467 is the bond energy value, multiplied by 4 comes to 1868. But we are making bonds, so I give that a negative sign. I then do the overall energy change by adding the 2 values together. 1359 minus 1868 comes to minus 509 kilojoules per mole. And of course, because we've got a negative sign, the reaction is exothermic. Because more energy is released on making the bonds in the products than is absorbed in breaking the bonds in the reactants, the reaction is exothermic. A second problem: calculate the energy change for the reaction between methane and oxygen to make carbon dioxide and water. Now, on this occasion, I think I'll give you the bond analysis. We've got methane, we've got oxygen, we've got carbon dioxide, and we have water. So I've shown the covalent bonds present in the reactants and the products. And that is the common practice in the exam papers. So from here, stop the lesson, calculate the total energy change, the overall energy change, and come back to check and correct when you are ready. Okay, so I'm going to reveal. Breaking the bonds, 4 carbon hydrogen comes to 1652, 2 oxygen doubles comes to 990. Add them together, give them a positive sign. We're breaking bonds. We're making 2 carbon double bond oxygen and 4 oxygen hydrogen. Choose the energy value, multiply by the numbers of moles, sum together, give that total energy value a negative sign because we are making bonds. So the overall energy change is the sum of breaking and making, so plus 2642 minus 3358 comes to minus 716. Exothermic, more energy released than absorbed. It has a negative energy change, overall energy change. This topic definitely benefits from practice, so use your textbook or online sources for problems. Make sure you've got access to answers to check and correct. Then move on to past paper questions, AQA GCSE. You'll find them in paper 1. If you find the lesson helpful, please recommend to a friend.